Yeah, welcome to today's lecture. We are looking at numerical methods for solving ordinary differential equations. Now, we've already seen solutions to differential equations in Math 105, that's Engineering Mathematics 2. Okay, and just to introduce ourselves to numerical solution, we want to recall our analog methods of solving, let's say, a first order differential equation. Like we have to find a solution to the differential equation y prime is equals to 3x, given that y at x0 is equals to 2. Okay, good. So we're saying that the solution to this system should be a function y which satisfies the differential equation y prime. Okay, and to solve this analytically, we can find a solution, okay, using a number of techniques, okay, depending on the form in which the equation can be put. So we can use the exact methods, we can use the separable methods, integrating factor approach, etc. Okay, good. So looking at this equation, we can easily separate it into the function what y of x and g of x. So as what dy is equals to 3x dx. Okay, then we find the integral of both sides. That will be the integral of dy is equals to the integral of 3x dx, which will give us y on the left side is equals to 3 over 2x squared plus c, the constant of integration. So that gives us the general equation, okay, or the general solution, okay. But given the initial conditions at x equals to 0, y was equals to 2, we can find c by substituting the value of y and x into the general equation to get what c is equals to 2. Hence the specific what solution to the system as what y is equals to 3 over 2 x squared plus what plus 2. Okay, so this gives us the specific solution or the specific function which satisfies the first order differential equation specified at the given initial value. Okay, so we refer to this as the analog system of finding the solution to differential. Now, the first point we have to know is that we are limited when it comes to the use of analytic solution or analog techniques. Okay, in what terms? In terms of its speed. It gets more tedious for some questions. You may have to spend close to like 5-10 minutes solving given differential equation. Okay, but real life problems are more complicated differential equations, and you need the solutions quick to make decisions. Hence, we cannot rely on analog techniques. Then again, some systems, what I mean is some differential equations cannot be solved using analytic method. Any of the analytic methods we have looked at in class. Okay, hence for an approximation technique, and numerical methods help us to address that challenge. Okay, so we say that method based on algorithm that will enable us to use a computer to arrive at what approximate solutions to differential equations. Okay, so amongst many techniques which we'll be looking at, which are the Hoynes, the Eulers, the Range-Kutta, to the other 4, the Taylor series method. The first of those techniques will be the Eulers method. That is what we are addressing in class first. Okay, so it says that given any first order differential equation, that is y prime of x, which is also written as f of x. Okay, f of x y. So over here, when you find, assuming I give you the y dx is equal ask you to solve it using the Euler's technique. The y dx is f of x. You understand? So it means that you rewrite this function as what? F of s over y is equal to 3x plus what? Maybe 2y. Are you getting it? So your derivative equation is always the function f. F means the derivative equation. You understand? So f at x and y, meaning f is a function of x and y, right? We know the general form of differential equation also. It's always given as y prime plus some a y is equal to p of x. Are you getting it? So we can rewrite it in this form. Good. Now it says you also need an initial condition which is y naught is equal to the value of y at x naught. In other words, when you are asked to find any differential, the solution to a differential equation, you need an initial value condition. Okay, we all know what IDPs are, right? So when you are given the differential equation, you also need to be given the boundary condition, okay, to assist you to find a solution. Then he says that to determine the iteration y at the given steps 1, 2, 3, 4. Yi means yi, okay, at I equals to 1, 2, 3, 4. Okay, that is it. So yi, when I is 0, you have this, when I is 1, are you getting it? Y2, Y3, Y4, Y5. Okay, it says using the Euler's technique, the formula for that iteration is going to be yi plus 1 is equal to yi plus the step size times the differential equation evaluated at the given points xi and yi. Are you getting it? So when I is 0, then we have y1 is equal to y0 plus h of f at x0, y0. Do you understand? Do you understand? When this is the general equation. So when I is 0, this becomes y0 plus 1, which will be y1, right? It's equal to y0, that's the initial condition, plus h times f of x0, y0. So you substitute the initial conditions into the differential equations here. Are you getting it? Then you break the step size here, and this will be the y at initial condition. You get it? Cool. Now when x or I equals to 1, then this is going to be y1 plus 1, which will be y2, right? At y1. By then you've already estimated y1. Okay? Plus f at x, f at x equals to x1 and y1. Already we have x1, we have y1, substitute. And you keep doing it over and over and over until you get to your final position, which is what? B. You understand? So you keep iterating from the first point till you get to what? B. Okay? Good. So let's take an example. Or you want to write? All of this. Okay. And then your notes from Lima's 2. Try to file all of them. It should be like a shelf. So file everything, level 100. You have all your notes there. So we have an example here. It says solve the differential equation y prime is equals to t minus y over 2 using the Euler's function given the initial condition y at 0 is equals to 1 and a step size of 0.1 where t belongs to the interval 0 to 1. It means we are iterating from 0 to what? 1, right? At the step size of 0.1. So we move 0, 0.1, 0.2, 0.3, 0.4, 0.5. So we get to what? 1. Do you understand? Cool. And the initial condition y naught is what? 1. And then s naught is what? 0. Is it clear? Is it clear? y naught is 1, x naught is 0. Is that clear to you? Yeah, that's the initial condition, right? Is it clear to you? Is it clear to you? Initial condition, is it clear to you? Okay, good. So that is the solution we have there. So it says the general function is what? Y at n plus 1 is equal to yn plus what? H f at x n comma yn. Okay. Now this is the general equation. It's in terms of x because we assume that y is a function of x, right? But it's not always that y is going to be a function of x. Sometimes y is a function of t. You understand? So in the case where y is a function of t, like this in this example, you change x towards t. You understand? Okay, so let's solve it. So at n equals to 0, now the first iteration, at n equals to 0, we have y 0 plus 1, which is y1. Okay, is equals to y0 plus your steps are f, h, then f of x0, y0. x0, we all know is what? 0, right? Initial condition. And then y0 is also what? 1. Are you getting it? So we're now going to solve that, putting the values in there. So y naught or y0 is 1 plus your step size is 0.1 into bracket. The function is what? T minus y all over 2. Okay, here we are dealing with t naught. You get it? So t naught is 0 minus we have y naught is also 1. Okay, over 2. You get it? And then you calculate for it to get 0.95. Is it clear? Is it clear? Is it clear? Some of you are not looking into my face. Is it clear? Yes. Okay. Then you repeat the process again. At n equals to 1, we're going to have what? We put it back into the function. So y at 1 plus 1, which is y2. Okay, is equals to y at 1, so y1 plus h f at what? t1 y1. You get it, because n is 1. You get it. Now y1 has been calculated here. Okay, and then what about t1? t1 we've moved from the first point to the next point. Step size. So it is s0 plus h. You get it? So anytime we move to the next iteration, we are moving with the step size. You get it? So now your t1 is going to be 0.1. Is it clear? So let's do the evaluation. y1 was 0.95, put it here, plus your h, your step size. Step size is always constant. The step size is constant, it's the t that will be moving. Okay? So 0.1 into bracket what? T is 0.1 minus your y1 is what? 0.95 over 2. Okay? Then you solve for it. Then we move on. So n equals to 3. You are dealing with, n equals to means you are dealing with y3 is equal to y2 plus h f x to y2. Okay? But we know y2, put it here, plus your steps are 0.1. Then your t has moved on again. So from 0.1 we move to 0.2. Are you following? Minus 0.91 over 2 is equal to 0.877. Are we clear on that? Yeah, so you keep doing the iteration until you get to t of what? T of 1. Okay, that is the final value. Okay, so write this down and then continue till you get t equals to 1. So we'll move on to the fourth approximation when n equals to 2. Okay, that obviously will give us 0.91 plus 0.1 into brackets. Your t here is 0.2 and your y2 is 0.91 over 2 will give us 0.87. Then we proceed with our approximation until t gets to 1. Okay, good. So at the sixth approximation, your y5 value is 0.8. Good. Now, programming, like we said, the essence of using numerical solution is to allow us to program and to get the computers to do this calculation for us, which means that we can also write a program to do this calculations we've been doing so far so easily with the press of a button. Okay, so for the very basis, we want to go into MATLAB. You can open MATLAB and then you copy this command in there. Okay, so once we write our command for the given function, that is, we first have to define h, your step size, which is 0.1. Okay, and then the interval from 0 to 1 over the step size 0.1, and then we write a loop, okay, to evaluate the function for a given value of t. Okay, so that will give us for I equals to 1 is to the length of t minus 1. Okay, y1 is defined, and then y subsequent y2, y3 and co will be yi plus 1 is equals to yi plus h, then the function which is the slope function, which is what, ti minus yi over 2. Then we end. Okay, and then you plot your function t against y. Okay, now this is the plot of the given function, as you can see on my right hand here. Okay, so clearly we can see that at y, at t equals to 0, y is equals to 1. At t equals to 0.1, y equals to 0.95. Okay, when you keep coming, the points show. Okay, so after all these calculations that we've calculated, with just a click of a button, you can see that we have a plot, okay, a demonstration of the solution of the function, right? But if we had used non-analog method, we had to calculate the point and now come to plot the function and then begins to do predictions, right? But on a click of a button using this program, we can easily make predictions based on the given graph we have at hand. Now, as your exercise, you want to try solving these two questions for me. You use the Eulers method to solve y prime is equals to 3e raised to the power negative t minus 0.4y, given the initial condition y at 0 equals to 5, step size is equals to 1, okay, and t defined over the interval 0 to 4. And then question 2 also, this time is y prime equals to 3 minus 0.4y, giving y at 0 equals to 5, and then step size is 1, interval is defined over 0 to 4. Okay, so solve it and then get back to me with any questions and I will address them for you.